In part 2, we're going to use the function generator to send a time varying voltage into a circuit with two different components, a resistor and a capacitor, and we're going to look at the voltage across the capacitor as a function of time using the oscilloscope. So, to set that up, let's take off this BNC to alligator clips cable, set it aside. Let's use our short BNC cable like we had it before, connecting the output of the function generator to the input of the oscilloscope. But since I want that signal to keep going onto the circuit, I'm going to attach it via T here, T connector. So that clips in like this, they twist, and then onto the oscilloscope. And there it appears on the screen. Well, this isn't even the signal we want. We want a 1 kilohertz square wave. So let's go to the 5K range. And let's go square wave button. We have this handy display here, 1400 hertz. So mess with it until we get, there's about 1,000. It's touchy. Turn down the fine controller to get closer to what we want. 1,000 is just a starting point. I don't think we need to be too worried about hitting exactly 1 kilohertz or 1,000 hertz. It's 1,000. Okay. 1,028 hertz. Let's get the display working on the screen. So it's way too bunched together. So to spread it out, we're going to turn the time div knob to the right. That looks pretty good. With a time division value of 200 microseconds. So 200 millionths of a second for each 1 centimeter square to the right. And let's see, we're still on 5 volts for each centimeter square vertically. And we want more like a 1 volt square wave. So let's decrease the volts, whoops, wrong way, volts per div to 1 volt per square, and then turn down the output level on the function generator until the top of the square wave and the bottom intersects with these 1 volt markings on the oscilloscope screen right there. So that's a 1 volt square wave because it goes 1 volt above and then 1 volt below the center line. Let's make sure it's centered vertically. Yeah. Okay. Good. Now we have here a breadboard. And a breadboard is for prototyping circuits. The horizontal bars at the 2 at the left and the 2 at the far right are all electrically connected vertically. So all the squares on the left are connected together and all the squares on the right are connected together. And then when you get into the middle 2 sections of 5 across, these are connected horizontally. So to make connections, we can, like to connect to this red pointer, the red wire, which will be the voltage from the oscilloscope, will come in here, and then we can put our resistor from here. Well, let's just set it up and you'll see how we're going to make a circuit. So if we want the red, make sure you can see this okay. Move it over a little bit. Prop it up. Good. Okay, so from the function generator, let's just plug it in. Function generator, it's going to continue on from the oscilloscope here. And then I'm going to plug it in like this. So from the red, or in the lab manual white side of the function generator, goes the resistor. I'm going to use here. This is a 100 ohm resistor. So I'll put one side, the polarity doesn't matter on these. So I'll put one side connected to the red, the high voltage, and then the other side in a random one of these rows. It's attached right there. And then I'll take a 0.1 microfarad capacitor. That's 100 nanofarads. And put it in the same row, so they're connected electrically now. And then I'll put the other side onto the black terminal here. So now we have a full circuit from red through the resistor. It's connected to the capacitor, back to black, and then that will go back to the ground of the function generator. So from the high voltage or the center cord in the BNC cable of the function generator, it goes through this T into this cable. Try to get it right. Into the red wire, through the resistor, through the capacitor, through the black wire, and then back to ground of the function generator. Then we'll take a oscilloscope probe and put it on channel 2 of the oscilloscope. So now we can observe the oscilloscope. One channel is coming straight from the function generator, and the other channel will look just at the capacitor. So I'll put this little alligator clip on the ground side of the capacitor, and I'll turn channel 2 on. Now it's a horizontal black line because there's no voltage difference across it. But once I put the oscilloscope probe on the high side of the capacitor, the high voltage side, then we'll see a signal. Make sure it's not pulling it out. Good. So now we have channel 2 here shows 50 millivolts per division, so I'm going to turn that down so we get it on the screen and make its position 0, so it's right over the channel 1. Now what's going on with, they're both a little bent here. I think it's the coupling. Here's the coupling. DC coupling. Go to channel 2. So my concern here is that channel 1 should just be a square wave, and channel 2 should show us, this is what we want to see, is the discharge of the capacitor. Let's keep going. So this looks like it's going from, we want to just see this discharge value. So let's increase the frequency a little bit, or that'll increase it a lot. And then we can decrease it over here. Oh, whoops. Let's go back to the 5K range. And we can increase the frequency, the knob here. Let's zoom in on the x-axis a little more so we only see a couple periods. Now as we increase the frequency, we'll get to a point where the capacitor is not being able to completely discharge. Here you can see the voltage drops and then sort of levels out at the bottom. If we increase the frequency to a point, it's not going to be able to totally discharge anymore, and it starts recharging right away. So right where we had it, let's zoom in again. And we can see how long it's taking. Let's turn channel 1 off. A little bit clipped. We can just look at channel 2 here and see exactly how long it's taking when we turn off the voltage here. How long does it take the capacitor to react? Let's make it take up as much of the picture as possible. Okay, put it right at 0. And move it down so it's centered. So we're going from, the divisions on channel 2 are 500 millivolts. So we're starting from 1 volt and going down to -1 volt. And how long is that taking? Well, the horizontal division is 20 microseconds. It's taking 1, 2, 3 and a bit of those to get down to what looks like 0 volts. We can use the cursors to try and see where it gets down to 36% of the peak. So it's starting at 900. It's starting at 1 volt. So and it's going down to -1. So that's a difference of 2 volts. So let's do 0.37 times 2. That's about 0.74. So 0.74 would be right at negative, what's 1 minus 0.74? Minus 0.25. So I'm going to make cursor 2 say minus 250 millivolts. Let's see if that does the right thing. So minus, you probably can't see this tiny, this is showing me the voltage at cursor 2 here, and I'm going to put it, there we go, minus 260 millivolts, and the time between them, delta here, is 14 microseconds. So that's some sort of estimation of tau. And of course that T1/2 is easier because we can just move to right where it intersects this 0 line here is right in between 1 volt and -1 volt. And then you can use the natural log of 2 to convert. And this delta T is 10.8 microseconds. Good. Okay, now we increase the resistance in the circuit. So I'm going to go from a 100 ohm resistor to a kilo ohm or 1000 ohm resistor. I'll just swap these out right here. Take that out and put this one in. Line it up with everything. Hard to see. There we go. Okay, what are we looking at now? We need to see more of the signal. So let's zoom out of the x-axis like this. And this is what I was talking about earlier, where the capacitor is not allowed to fully charge or discharge before the square wave switches from plus to minus. Let me separate these two things a little bit so we can see both of them not right on top of each other. Turn the cursors off for the time being. Okay, so we want to allow the capacitor to charge and uncharge. Oh, I'm running out of battery. I have to pause this. So what we're going to do is decrease the frequency, increase the amount of time we have. So let's decrease the frequency. Right? I mean, we can go the other way. We might as well check it while we're here. Increase the frequency. It doesn't look any better. It looks more like a triangle wave. As we decrease the frequency and give it more time, it starts to look like that characteristic charge, sort of decharge curve, that exponential. And from this, we can see it's not charged, fully charging and discharging. We could probably still get a time constant out of it, but let's find the frequency where it looks like it's fully charged. That looks pretty good. Oh, look at where we are. Back at 1 kilohertz. Okay, so from there, we can get rid of the channel 1 again, because it's just the square wave. And get one cycle of the, in this case, the charging of the capacitor to take up the whole screen so we can get a better measurement. So I'll move it a little to the left, and I'll move it a little bit up. So now it's starting at -1 volt, and it's going up to +1 volt. And how long does that take? Well, let's move it a little bit to the right. So we get right on a line. Of course, we could also do this with the cursors. You don't have to use the graduations on the screen. So we're going from -1 through 0 to +1, right? 1, 2, 500 millivolt jumps, 1, 2, 500 millivolt jumps. So the amount of time it takes to go to halfway is right here, and I'm going to use the cursor to find that number. Scroll over. Halfway is going to be right at 0 volts on the screen. So the cursor is right around 0 volts on the screen. And the time, well, you can move the other cursor over. While we're using the cursors, might as well. Whoops, where'd that go? So that one's there. Select. There. Now this one, I'll move over here to -1 volts. And the delta is 77 microseconds. So when we stayed with the 0.1 microfarad capacitor and increased from 100 ohms to 1,000 ohms, or 1 kilo ohm, the time that it took to charge the capacitor to 1/2 of its value went to 77 microseconds. It says US right there. And of course the discharge cycle would be similar. And the next step would be to change the capacitance. I guess we'll try it, and if the camera dies in the middle, then I'll just add another video. Let's change the capacitance. Let's go back to the original well, we'll do all 4 combinations. So I'll change the capacitor, and then we can go back to the original resistance with the new capacitance. Put the resistor into the circuit, reattach the oscilloscope. Okay, hopefully you're keeping track of all this. I'm not writing anything down. Terrible scientific practice. Okay, so this is a 0.27 microfarad capacitor, or a 270 nanofarad capacitor, still with the kilo ohm resistor. Now let's adjust the oscilloscope, zoom out in X, and add channel 1 back in so we can see what's going on. Move them out of each other's way a little bit. Now it's not fully discharging or charging, so let's decrease the frequency even more to allow it to fully charge and discharge. That looks better. It looks like it's barely able to charge and discharge. Good. This says 387 hertz for the square wave, for both of them, I guess. And you can see, I'll turn the cursors off because it's getting a little cluttered. So here's the voltage across the capacitor in blue once again, and the signal from the function generator in yellow. They're on different scales. Let me put it to the same scale so it's not so confusing. Now they're both at the 500 millivolts per division scale. And let me show them overlapped. So I think that sort of makes a little bit more sense. This is, the yellow is the voltage being supplied, and the blue is the voltage across the capacitor as it charges, discharges over and over. Okay, so we're done with the square wave, and we're going to look once again. We're still on 500 millivolts per division at the voltage across the capacitor. Zoom in to increase our accuracy here. So I'll use the cursor to find how long the voltage on the capacitor takes to go from fully discharged, like from -1 volts, to half of its max value, which would be at the 0 mark here. That's halfway between -1 and +1 lines. And the time it shows between the cursors is delta 210 microseconds. And that was for 1 kilo ohm resistor and 0.27 microfarads. Now the last thing to check is to go back to the original resistor, which was 100 ohms, and I'll plug it in one side in the red, the high side from the function generator. Other side goes to connect to the capacitor. Okay, so we decreased the resistance in the circuit, in the RC circuit, and you could see an immediate obvious difference in the charge cycle of the capacitor. It has plenty of time to charge, and then it's just sitting there charged. So we could zoom in. Let's change the frequency so that it looks like all the other frequencies where it was just barely charged. So now we're going to increase the frequency again to not give it so much time just sitting there, so it looks like the other curves we had. That looks about like what we had before. So now I increase the frequency, so I'm going to zoom in on the oscilloscope by turning the time per div knob. And we'll go through the same. It's going to look the same, but the numbers are going to be different because now the time per divisions is set to 50 microseconds. I didn't check what it was before. Sorry. Something like 200 microseconds. So I've zoomed in for this last case with the 100 ohm resistor and the 0.27, the larger capacitor, 0.27 microfarads. Okay, so move it over a little bit. Whoop, jumped on me. And then I'll move the other cursor, which is right here, until to the midpoint. Now let's zoom in even more. Yeah, I'm not gonna do that. To the midpoint, looks to be right here. And delta is saying 28 microseconds. And that would be T1/2. Okay, I think that's it. 9. Change the amplitude of the square signal and repeat step 7. Okay. Change the amplitude. So let's just repeat this step here. Let's turn on channel 1. Let's go back to this resistor seemed to work a little bit better. I'm not sure why. Okay, so we've gone back to the higher resistor and the higher capacitor. 1 kilo ohm resistor, 0.27 microfarad capacitor. And let's go back to how we had it set up. Now we don't have enough time to charge and discharge the capacitor. So let's turn the frequency down to give it more time. Okay. So there's more time to charge and discharge the capacitor. Now, what am I doing here? Increasing the amplitude of the square wave. So if I increase, that's this knob here, output level. And try to do it so you can see the screen. Increase. And let me turn everything down. So this is 500. I'm going to go from 500 millivolts per division. Get rid of the cursor. Now I'm at 1 volt per division, and I'm going to turn up the output level from the function generator. I don't know. Is that what you expected? Let me know if you need me to take any more data.